Now let's shift gears a little bit to talk about alternate electrophiles rather than alternate nucleophiles. What we're going to discuss now is a series of reactions which are known as conjugate additions. These are reactions with carbonyl groups that have electrophilic carbons at the beta position. So one example of a compound that would react this way is this unsaturated ketone. Remember that we first explained the electrophilicity of the carbonyl group with resonance by showing this resonance form that has a positive charge at the carbonyl carbon. This makes that electrophilic. If we add unsaturation adjacent to the carbonyl group, we can draw an additional resonance form which also has a positive charge at the beta position. That means that these compounds act as bidentate electrophiles. They are electrophilic both at the carbonyl carbon and at the beta position. We'll see that different types of electrophiles react at these two different positions. The carbonyl carbon tends to collect hard nucleophiles or very reactive nucleophiles like organolithium and organomagnesium reagents, as well as things like alkoxides. The beta position will collect what are known as softer nucleophiles or more stable compounds. These are going to be things like large atoms, so sulfides and thiols. Organocuprates will also react at the beta position, and these will also be excellent reacting positions for doubly stabilized enolates like we saw in the previous video. To reiterate, very reactive or strong nucleophiles will tend to add to the carbonyl carbon in what we're going to be calling 1,2 addition. For example, this unsaturated ketone will react with phenyllithium followed by workup with water to give this tertiary alcohol. Why is this called 1,2 addition? Because if we look at where the changes have happened in our product, we've added two groups to atoms 1 and 2, two adjacent atoms. Larger atoms, or softer, more stable nucleophiles, will tend to do what's known as 1,4 or Michael addition. One example of this is the reaction of alpha-beta unsaturated carbonyl groups with organocuprates. For instance, if I take cyclohexanone and treat it with diphenylcopper-lithium followed by an acid workup, I'm going to add the phenyl group to the beta position relative to our carbonyl group. The way this reaction works is as follows. The nucleophile will add to the electrophilic beta position, which will produce an enolate as the final product. Upon treatment with acid, this enolate will pick up a proton, leading to 1,4 addition. The added nucleophile and the proton are separated by two additional atoms. Under these conditions, this enol will rapidly tautomerize back to the ketone, giving us our product. The question that this raises here is how do we separate this into 1,2 versus 1,4 addition? How do we predict which one happens? In these reactions, we're going to refer to the nucleophiles and electrophiles as Michael donors and Michael acceptors, respectively. Here are some nucleophiles which are good Michael donors and will cleanly and quickly undergo fast 1,4 addition. Doubly stabilized enolates, like acetoacetic esters, malonic esters, and derivatives thereof, will tend to add 1,4 rather than 1,2. We'll also see compounds that are similar derivatives of carbonyl compounds, like for instance this ketonitrile. Nitroanions will also undergo this reaction as they are quite stable anions. Finally, we have single atom nucleophiles, which are larger and softer and less reactive, like sulfur compounds and organocuprates. These will react with Michael acceptors. The compounds I'm going to show here all have beta electrophilic carbons. Unsaturated carbonyl derivatives, here X is not necessarily meant to represent a halogen, but any member of the carbonyl family. Carboxylic acids, ketones, aldehydes, acid chlorides, and amides will all react like this. Nitriles are also functional derivatives of carboxylic acids and will work the same way. Nitro compounds, which are unsaturated, are also Michael acceptors. Notice that there is one electrophile that's missing from this list. Regular enols and enolates are poor choices for these reactions. They are a little more reactive than the distabilized enolates, but significantly less reactive than organometallic reagents like phenyllithium or methylmagnesium bromide. These are bad choices for these reactions because they tend to give mixtures of both 1,4 and 1,2 addition. Let's do some practice. Take each of these and draw the product of each of these reaction sequences. Take a moment to do this and we'll check your work when we're done. The first reaction would give us a phenyl group substituted at the beta carbon of the ring. The second reaction would end up adding diethylmalonate to the beta position relative to the nitrile group. The third reaction is actually a variant of the malonic ester synthesis, where we have a decarboxylation to give a substituted carboxylic acid derivative. Let's do a little bit of mechanistic practice here by looking at the reaction of the polymerization of superglue. Here's the structure of superglue, which can be polymerized in the presence of a trace amount of water or other nucleophiles. What I'd like you to do here is show the mechanism of this polymerization process and predict the structure of the polymer that results. Take a moment to do this. We'll compare notes when you're done. The way we would start here is by noting that methyl 2-cyanoacrylate, the starting material for superglue, is a Michael acceptor. Therefore, in the presence of a nucleophile, we're liable to have conjugate addition take place to give an enolate anion as a reactive intermediate. This is a doubly stabilized enolate, as that negative charge can be delocalized both through the electron withdrawing nitrile and through the ester group. That means this is a good Michael donor. So in the presence of another equivalent of our starting monomer, we're going to have another conjugate addition to happen, which will produce another doubly stabilized enolate. This process will continue until we get a polymer with this repeating unit. Incidentally, this is why superglue will instantly polymerize together your fingers if you get it on your skin. Your skin is moist and contains many nucleophiles. Pressing your fingers together creates a very thin layer of the glue that will instantly polymerize, bonding your fingers together for several days. There's one more good application to this type of reaction, which is known as the Stork-Amine synthesis. In the Stork-Amine synthesis, I'm going to start with a ketone, treat it with an amine in the presence of an acid catalyst, followed by an unsaturated carbonyl compound, followed by an acid workup. And in this case, I'm going to do a reaction that looks a lot like a conjugate addition of an aldol enolate. So this is interesting. What I'd like to know here is what exactly is that amine doing? We know from our previous discussions that it isn't very efficient at making an enolate, so its role in this reaction must be different. If we go back to one of the previous chapters, we'll notice this, the reaction of a disubstituted amine with a proton, as the formation of an enamine. If we look more closely at the enamine, we can see that the enamine has a resonance form, which puts a negative charge at the alpha carbon, making this nucleophilic, very similar to an enol or an enolate. This nucleophile can then undergo conjugate addition to an unsaturated carbonyl compound to give this enolate as a product. Here, if we treat this compound with H3O+, we're going to protonate and tautomerize the enolate back into a ketone, and we'll also hydrolyze the iminium ion, releasing the amine, regenerating the other carbonyl group. In our next video in this sequence, we're going to discuss the applications of these reactions in synthesis problems.